Hello everyone, welcome to 2023 fall edition of the Math Club. This is the first lecture and it will be given by Aaratrick Basu of Math third year. He is interested in hyperbolic geometry and topology in general, along with its connections to algebra. And today's talk will be on hyperbolic geometry, leading up to hyperbolic surfaces, and motivating the concept of Fuchsian groups from hyperbolic surfaces and why they are important. So over to you, Aaratrick.
Thank you. So, I've written down the plan here, essentially just the title. So, we begin with some motivation for why we even do hyperbolic geometry. Then we discuss hyperbolic geometry properly. Then we move on to hyperbolic surfaces, and finally we end with Fuchsian. So, what is why do we do hyperbolic geometry and what is it in the first place? So, before we begin, let's recall some elementary Euclidean geometry from high school. So, what we mean is geometry in the plane, R2. Right? So, what do we understand when we mean Euclidean geometry? We mean study of polygons, triangles, squares, quadrilaterals, other quadrilaterals, their angles, areas, stuff like that, right? More abstractly, we can ask the question of, can we do geometry on arbitrary two-dimensional spaces for an appropriate definition of dimension and appropriate definition of space? So, for that we need to know what a two-dimensional space is, and that is what we call a surface. So, what is this? This is a topological space X satisfying certain regularity conditions, and more importantly, which is locally R2. So, what does this mean? This means that if X looks, say, somewhat like this, then given any point P on X, you can find a small enough neighborhood, call it U, such that U is homeomorphic to some U hat open in R2 for every point P. So you can find, so basically what this condition is saying is that if you live on X, then at least locally you won't be able to distinguish whether you are living on X or living on R2 as far as topology is concerned. So this is what I meant by a two-dimensional space, a surface, and so we want to do geometry on such spaces. So how do we do geometry? So the basic idea of geometry is to measure lengths, right? But we usually don't ask for only lengths, we ask for angles. So we want our surface, let us call that S, to come with a good enough notion of measuring angles, which is just the inner product on the surface S, and we then call our surface to be Riemannian. That if it comes with a well-defined notion of angle. So once we have the notion of angles, we just simply define length by the familiar formula. Norm of V is half of the, square root of the inner product of the vector with itself. And so we can do geometry on the surface now. But this is in some sense too loose. We want a stricter notion. And so, we also speak of Riemann surfaces. This won't really be clear why we define this right now, but I'll need this notion later. So, we'll just define it for now. So, this definition is essentially the same as this, but the regularity conditions are the same, but instead of asking for that it's locally R2, we say that it's locally C. So, in the sense that we'll ask that U be conformally equivalent to some open U hat subset of C. So what does conformal equivalence mean? Conformal equivalence simply means that you have a holomorphic map going from U to some open domain U hat in C, which is also a bijection. So it's a result from complex analysis that any holomorphic bijection is also satisfied that the inverse is holomorphic, and so this notion is well defined. And so if we put this condition, then we obtain what is called a Riemann surface. So when we go to hyperbolic surfaces, we will see why this is important. But for now, we just needed this definition. Now, what do we mean by hyperbolic geometry? So hyperbolic geometry essentially boils down to speaking of geometry of negatively curved spaces in two dimensions, negatively curved surfaces. So for that, we want to speak of curvature. But before that, we also need the following elementary results from surfaces. So here, so this is not usually not a first result, but we'll only need this statement, classification topology. So this says that given a surface S which is compact and oriented, so compactness I assume everyone is familiar with, oriented simply for our purposes means that we can have a continuous assignment of normals for all points of the surface. So I mean by continuous I really mean smooth, in the sense that at every point there is an inward and outward normal, and we consistently choose some assignment such that the assignment is smooth over the entire surface. So if you have a compact oriented surface, say without boundary, then S is homeomorphic to Sg, which we define to be the connect sum of G tori. So this is G many or G greater than equal to 1, and thus simply the sphere. So S2 denotes the sphere if G is equal to 0. So what is this saying? This is saying that you start with some compact oriented surface S and assume that the boundary of the surface is empty. So S does not have any boundary components. Then there exists some G greater than equal to 0 such that this happens. S is homeomorphic to Sg, where the definition of Sg is as follows. So what does this look like? This looks like the following. This. Is this visible by the way? It's not visible. So you basically imagine a G-hole donut. So this is what some G. It doesn't matter topologically how we draw it. We could have drawn it like say G holes with some center, but I mean, that doesn't matter topologically. So this is Sg, and the sphere I think everybody knows. So this is the theorem. We can actually strengthen it that if say del S is not equal to phi, then there exists G and B greater than equal to 0, such that S is homeomorphic to SGB, where SGB is exactly what you obtain from SG by removing B many open disks. So what you are essentially doing is you are cutting out open disks from your surface so that you basically are left with a boundary component. So if there is B many boundary components, it's the same as removing B many open disks. And this is sort of the entire thing. So this is the classification, the topological classification of surfaces. We'll actually discuss some kind of analog for this for Riemann surfaces later, but this is what I need for now. So what do we understand by this theorem? What this theorem says is that if we want to understand only the topology of surfaces, it's enough to understand these SGBs. And I mean, if you can understand SGs, you more or less understand SGBs, and so it's fine if you only understand the SGs, right? But so is that it? Is surface theory over? Well, not really, because we actually want to do geometry, right? So this is only talking about the topology. So what we do is we define some invariants. So already we have two invariants, G and B, right? So this G is called the genus, and B is the number of boundary components, right? But we prefer to work with a different invariant, sometimes called the Euler characteristic or the Euler number. This is visible, right? Number chi of SGE. So we will define it like this, but it's a result from elementary algebraic topology. It is also the alternating sum of the petty numbers. I mean, it's proven that at least for surfaces SGB, compact oriented, this is a finite sum and it's well defined and is in fact equal to this, right? But we really don't care about this for the purpose of this talk. This will suffice. So if it happens that B is 0, if our surface is without boundary, then we actually get that chi and G are more or less on the same level. We can get G from chi and the other way around. But we, I mean, sometimes prefer to work with this. Why? Well, it is a fact from covering space theory that, maybe I'll erase this, if, theorem again, if chi of S, where S is a surface compact, is less than equal to 0, then the universal cover S tilde. So this is simply a topological space which in some sense covers your surface and is without holes. So it's technically called simply connected, is homeomorphic to R2. Right. So we'll meet this again later when we do hyperbolic surfaces. So all of this is building up the hyperbolic surfaces in some sense. But yeah, so this is the result that we want. That if chi S is non-positive, then your universal cover turns out to be the plane. So in some sense, your topology is actually coming from the topology of the plane and you project it down, right? But in fact, we'll strengthen this to somehow say that it's the geometry of the hyperbolic plane which can be projected down. But before that, let's talk of curvature, right? We need to talk of curvature. So, curvature. So, intuitively curvature is obvious. Curvature, at least in 2 dimensions, means that we intuitively understand that the plane is flat, it has 0 curvature, and your surface is positively curved if it bends away from the plane, and it's negatively curved if it bends inward towards the plane, right? But we need a proper definition, and there are actually multiple definitions, and in higher dimensions they actually give several different numbers that are all useful, but at least for 2 dimensions we can give this sort of simple-minded definition, like S be a Riemannian surface, then if X is in S and area, then K of S, K of X or X in S is defined as area of some disk of radius R based at X, centered at X, should be, not make a mistake here, so should be pi times R squared minus 1 over 12 Kx R to the 4 plus O of R to the 4. So what is this saying? This is essentially saying that if you have a flat surface, Kx should be 0 everywhere, then you reduce to the case pi r squared. And if it's not flat, then at least to order 4, if you pick a small enough disk, centered at your point, then the area should locally look somewhat like this. It should be pi r squared minus something, right? Where is this 1 over 12 coming from? Well, we want the sphere to have constant curvature Kx identically equal to 1 for x in S2. We want this, and to normalize for that, we get the constant minus pi over 12 essentially. So now, what do we mean by negatively curved spaces? We mean spaces or surfaces for our purpose where Kx is a constant negative number which we can scale to be minus 1 because, this requires a proof, but you can sort of believe this, I think, that if you have some Kx to be say minus alpha, then you can scale your inner product in an appropriate way so that Kx becomes minus 1, right? So now it's a question of whether there even exists such a thing, right? Whether there exists a surface where Kx is minus 1 everywhere. So this was an important question in the 19th century, which was answered by Russian mathematicians Bolyai and Lobachevsky. I think I've butchered their English spellings, but these are Russian names. So Bolyai and Lobachevsky, they actually constructed surfaces in some sense that had Kx equal to minus 1 everywhere. For example, I think one construction was the one for Gabriel's horn, where you take the graph of x comma 1 over x and x comma minus 1 over x, and for x greater than 0, and rotate it around the x-axis to get this kind of a horn-like thing. And it can be shown that this is actually a surface that satisfies our regularity conditions, and also Kx equal to minus 1, right? With some appropriate inner product. But the problem with this is, yeah.
So in the definition we are finding Kfx.
Right.
So Drx is an open body tangent plane?
Yes. It's a disk around it. Yes. So I don't want this talk to be at such a high level, so I didn't mention all that. But yeah, that is what it is. But yeah. So the problem with this is that it's not a good embedding in some sense, because first of all it diverges, it flares out around x equal to 0, right? It goes to infinity. And so people weren't really ready to accept this kind of thing. And so later, this is properly moving to hyperbolic geometry. We come to Poincaré's half-plane model. Plane model. So what do I mean by model, by the way? A model is essentially any surface which has curvature -1 and which is simply connected. Because I mean, hyperbolic geometry in some sense is about the geometry of a simply connected negatively curved surface, and then we can get any other thing as a hyperbolic surface, which I'll talk about later. So this is the space is H2. Z in C, such that mod Z in Z is strictly positive. And the metric is given at the arc length level as by y squared. This can also be written as a conformal metric, mod z squared by in Z squared. But we don't need what a conformal. We don't need to know what a conformal metric is for today's story. So what is this saying? This is essentially saying, if you recall from high school calculus, for the Euclidean plane, we know that your arc length was given as right. So we are scaling by the y coordinate. So if I draw the picture, this is x. Right. So in your Euclidean picture, everything was somehow uniform. That whether you measure distance here or here, it would be the same. Say a horizontal, constant y-level lines. But in this particular metric, if you could measure the length of this segment and this segment, this would be much higher because the y is smaller, and so this 1 by y squared is larger, right? So we get that this is bigger, and so we already see that this is somehow different from our usual geometry of the Euclidean plane. And we'll try to understand this geometry throughout this talk. And so let's move on. How do we understand this geometry? Well, we want to measure distances between points, right? So how do we do that? Well, we are given a metric at the arc length level, and so we should measure lengths of curves first. So let gamma from 0, 1 to x2 be a piecewise smooth curve. Then according to this metric, the length of gamma is just integral 0 to 1 mod of gamma prime norm. So this is in the hyperbolic metric, this is in the usual Euclidean metric by because as you see this mod is in the usual C sense, like whatever we do in C usually, by in gamma dt, right? So this is the length of a curve. So basically, if you are given a curve, that's how you measure this length. You take the derivative at each point and integrate with this kind of formula, right? So now we can measure lengths of curves. Well, then we define the distance between 2 points, z and w, both in the upper half plane, to be simply the infimum over all gamma joining z and w and piecewise smooth mod gamma. Right. So this is in the hyperbolic metric. This is also in the hyperbolic metric, and I'll drop the subscript from now on. So this is the metric. This is the actual distance function on your H2, right? So we now know how to measure distances. In some abstract sense, right? But we don't even know how to compute this. We don't even know. So, for example, if I contrast this with Euclidean geometry, that begins with your axiom that given any 2 points, there's the shortest path joining them is the segment of the line between them, right? But here we are starting geometry from a different perspective. We are starting it from this arc length function and then measuring length of curve, and from there are we getting the distance function between points. So how do we get from here to here? In some sense, we want to speak of geometry here on the same level as Euclidean geometry. So the way we do that is we want to find out things like this. We want to find out what are called geodesics. So what are geodesics? Geodesics are the, our geodesic between 2 points is a curve, piecewise smooth, that has the shortest length. So yeah, but it need not be unique. For example, if you take the circle, then between any two diametrically opposite points with the usual metric, of course, both this and this will be a geodesic. And if you take the puncture plane, let's remove 0, so this is just R2, then say between these 2 points, any such segment is, tries to approach to the geodesic this horizontal segment, but you can never get there because this infimum is the horizontal distance between them, but you can never get a curve between these 2 points that attains that, right? So we want to know whether this kind of thing happens in H2 with our metric. So how do we do that? Well, here is where the theory sort of diverges from high school geometry, in the sense that we will understand this geometry using the structure of symmetries of this geometry. So what do I mean by that? We will understand isom H2. We'll try and understand isom H2 and we'll see how that leads us to the geodesics of H2 and in fact more information about the geometry. Great. So what is isom H2? Well, a priori we have no idea what this is, right? So we start with maps like this. T, so this is a collection of all T such that T Z, so this is T is a map. Tz is equals to Az plus D by Cz plus D such that A, B, C, D are real and AB minus BC is 1. So this is a subset of the set of all Mobius maps, but if you restrict to such Mobius maps where the coefficients are real and AD minus BC is 1, so some determinant looking condition, you can check that all such maps actually go from H2 to H2. So if you input a point in the upper half plane, it will also land in the upper half plane, right? So how does this work? This works because you have imaginary part of Tz is equal to imaginary part of Z. So this is a simple computation. You can do this yourself. So if imaginary part of Z is strictly greater than 0, so is this, and so we have a good map from H2 to H2. So why this particular set? Well, let me pull this up. We essentially do this because we know what this is. PSL2R, which is SL2R mod tilde, where SL2R denotes the set of all 2 by 2 real matrices with determinant 1, and tilde is the identification that A, B, C, D and is equivalent to minus A, minus B, minus C, minus D. By the way, this is all visible, right? Right. So you identify basically matrices up to sign. You don't care whether all the coefficients have the flipped signs. If you do that, you get the projectivized special linear group PSL2R. And why do we care for this? We care because if you flip all the signs here, you have the same map, right? And so what we have done is we have essentially said that PSL2R is the same thing as the set of all T that I described above, right? And so what we have done is we have identified a familiar matrix group. A lot was known about PSL2R than about isom H2. So we have identified a familiar matrix group to a group of maps from S2 to itself. Now, why is this important? Well, this is important because of the following result. I'll not be proving this, but the proofs are more or less, I think, obvious. I mean, you just sit down and compute. The first thing is that PSL2R acts on H2 by diffeomorphism. Right. Why is this? Because you already have an action, right? You take a PSL2R element and associate this map, and this acts by diffeomorphism because you can already see that T, if T is of that form, then T inverse Z is also of that form. And in fact, T prime Z looks like 1 over Cz plus D whole squared, which is never 0 for Z in the upper half plane, right? And so T has a non-vanishing derivative, and so does T inverse, and so we get this. In fact, we can do better. The action is by isometry. How do we do this? We do this by just taking some curve gamma from 0, 1 to h2, and then we apply T and see that under the, where did I erase that? So if I write that down again, gamma equals integral 0 to 1 mod of gamma prime by gamma dt. This formula is T invariant for any T in PSL2R. And so T acts by for any T in PSL2R, it's an isometry, right? So starting from essentially nothing, only length of curves, we have identified that PSL2R is a subgroup of isom H2. Right? It's a subgroup. I mean, okay, well, it's not really clear whether it's a subgroup yet, it's just a subset. But, well, in fact, one can show that if you have these results and some computational results which are mentioned at the end, then you can show theorem that isom H2 is generated by PSL2R and the map Z going to minus Z bar. Right? So what is it saying? It's saying that if you start with an arbitrary isometry simply means that it preserves length of curves or distance of points, then it's actually some composition of a PSL2R element and this anti-conjugation ring. Right? So what does this tell us? We know from this diffeomorphism kind of thing that because T dash Z is in fact actually positive, I mean maybe not positive, yeah. It's actually orientation preserving, and we know that anti-conjugation is orientation reversing, and so we actually also have that corollary isom plus of H2, so this is the orientation preserving isometries of H2 is actually isomorphic to PSL2R. So starting from nothing, we've actually managed to identify the orientation preserving isomorphism H2, and we in fact also know that any other isomorphism is some composite of this and this anti-conjugation. Right. So pretty good. But well, we wanted to know what the geodesics are. So how do we do that? So that theorem. Geodesics in H2 are generalized semicircles orthogonal to the x-axis. So what does this mean? Let's just draw the picture. So this is the x-axis and the y-axis. And what I mean are half lines like this and semicircles like this. So basically the center of any such semicircle should be on the x-axis. So how do we prove this? Well, we can actually show this, this is an easy exercise, that any such curve can be, the segment between any 2 points on such a curve can be transferred to a vertical segment on the imaginary axis, and you can show by hand that the geodesic between any 2 points on the imaginary axis is actually the vertical segment between them, and hence we have that these must have been the geodesics, because we already know that PSL to R acts by isom plus away. So the transfer here, that this segment going to this segment or this segment going to this segment, is actually by a single PSL to R element. Right? We can do that. That's an easy exercise. So we've accomplished our first target, that we have identified what the geodesics are. So now we know that the geodesics in H, what are the geodesics in H2, and that they are unique simply because of these kinds of curves. So what do we do now? Well, we want to study some other concepts like, say, areas or what do the polygons look like. So before that, we have one other interesting result. Write that here. The topology induced by rho h2 is the same as, or rather, is homeomorphic to the Euclidean topology. So what is this saying? This is saying that we already have a distance rho h2 between points on the upper half plane, and we also have a distance rho r2, right? Just the distance on r2 restricted to h2. Both of these make h2 into a metric space different, because we know that rho h2 and rho r2 are not the same. What this is saying is that the topology induced by these metrics are the same, in the sense that if you start with any ball under this metric, you can actually show that such a ball is also a metric in this, also a ball under this metric with some different center and radius. And so what this theorem essentially says is that our metric doesn't affect the topology at all. It's only the geometry which is affected. And so, I think this is fascinating that we started with some completely different metric and we still ended up with the same topology. But the geometry is different, as we have already seen. And in fact, there's a more striking sort of difference. I should draw. Recall Euclid's fifth axiom, the parallel postulate, that given any point and the line such that the point is not on the line, there's a unique line parallel to that line passing through that point, right? But well, say you start with this geodesic and you start with this point Z. Then what you can do is this geodesic, this will go somewhat like this will go somewhat like this. These two geodesics are both parallel to this, right? Because they're both orthogonal at the same points. So they are both parallel, and so we see that the fifth postulate, the parallel postulate, is valid. And so this geometry is fundamentally different from the Euclidean geometry, right? So this sort of says that okay, we should actually revisit some familiar geometric concepts, trigonometry. Although I think almost everyone here doesn't like trigonometry, but we should revisit it to some extent. So before that, let's actually define what a triangle is. So basically this is some computation in H2. So what is a triangle? A triangle, maybe I should draw that figure. A triangle is simply given any 3 points, you join all pairs, like the 3 pairs, using the geodesics between them. Right? So this is what a triangle in H2 looks like. This is one triangle, there's more. If you allow for points on the boundary, the real axis, and also infinity, so we define del h2, the boundary of h2 to be R union infinity. So you have triangles like this, and also triangles like this. So believe it or not, this is also a triangle. In fact, what you can do is, because this is one vertex, this is one vertex, and the large vertex is infinity. But using a PSL to our action, we can redraw it as something like this. So these are, I mean, this has no vertex on the boundary, this has one vertex, and this has two. And oh, yeah, this has three vertices on the boundary. In fact, you can also draw a figure for two vertices on the boundary. Right. It's basically this. Right. So these are the kinds of triangles. And so we want to do some computations of triangles and other polygons.
I have a question.
Yeah.
Why don't we work in some kind of projective case and then you can easily constant integration?
Yeah. So this is essentially just, I mean, talking of C hat, and then, I mean, you have C hat and you want the upper half plane, so you cut the sphere in half, and that is when you get the boundary to be R union infinity. That is what we are doing essentially. But we don't need to know this to do this. We can do this with a definition. So before I talk of the computation, we also speak of one other model. So maybe over here. So, like I said, a model is anything which will be simply connected and has constant curvature -1. So we can also have the disk model. So this is also given by Poincaré, sometimes called the Poincaré disk model. So the space now is D2, the unit disk, Z in C, such that mod Z is 1, and the metric DS2 is now is 4 mod dz squared by 1 minus mod z squared whole square. So this is the metric now. Where does this come from? This comes from the fact that we have this bijection f from h2 to d2 that sends z to zi plus 1 by z plus I. You can check that this is a bijection first of all, and then what you do is you demand that this is an isometry. And so you start with 2 points in D2, go to the three images, compute the distance and say that, oh, the distance between those 2 points in D2 should be the same as this. And that leads to this arc length level metric, and we'll actually show what the point level metric is there. And so there's one other way of looking at this. So it can be shown that any conformal metric on the unit disk that has PSL to R as a group of automorphisms must be proportional to this, and if you want to have curvature -1 constant, then the factor proportionality constant must be 4. So I mean, we won't work at that level here, but just an aside. So let's actually do some computations. And one is that rho h2 of zw. So we didn't know what this was applied, right? We don't have, but what this formula will tell us is that we don't have to go back to shifting geodesics to the imaginary axis all the time. So log of, sorry about this, mod z minus w bar plus mod of z minus w by mod of z minus w bar minus mod z minus w. And using that Cayley map, you can actually shift to the unit disk and get a similar looking formula. I'll spare you the pain. And rather, what we'll do is, let's look at a circle, right, of radius in the hyperbolic metric R. Then, using the length of curve definition that I have given, you can show that the circumference is actually 2 pi sine hyperbolic of R. This is visible, right? And the area is 4 pi sine hyperbolic r over 2 square. So why did we introduce that model? These computations, okay, maybe this can be done with, okay, no, even this is easier in this disk model, because what you do is you assume that this is inside the disk, and so this curve has a particularly nice parameterization. Just take gamma to be some capital R, e to the 2 pi I t, right, with the center at the origin, and where R is the Euclidean equivalent of R, the small r, and so then you do these computations C and A, which is easier here. Oh, I think I didn't define area. Define area. Sorry about this. Area. So if S is a subset of H2 or T2, then mu of S is defined equals to 1 over y squared dy dx if it's in the upper half plane, and it's 4 over 1 minus r squared whole squared r dr d theta if it's in the disk model. So if the integral exists, is that S has an area, and you can check that the integral exists for a circle, and you can compute that it exists. And what we can do is we can geometrically compute the area of a triangle. So if our triangle has internal angles alpha, beta, gamma, and say this is BC, right? So internal angles alpha, beta, gamma,
I think
and
you should say not generally.
this. Sorry about it.
Use that.
Next one. Oh, yeah. Right. So if you have internal angles alpha, beta, gamma, and length, so A, B, and C are measured in the hyperbolic metric, then you can show that mu of the triangle delta, let's call that delta, is actually equal to pi minus alpha plus beta plus gamma. So this is sometimes called the area formula in hyperbolic geometry. The Euclidean analog of this does not exist actually. The spherical analog of this is pi plus alpha plus beta plus gamma. Right? So what does this say?
How do we define upper beta?
Internal angles. Angles between these two units. We just take a tangent circle. Right. So what this says is, in hyperbolic geometry, the internal angles of a triangle sum to something less than pi. Right? So that is another contrast between H2 and R2. And in fact, you have this formula. Oh, maybe I should write that. Cos hyperbolic of C is cos alpha cos beta plus cos gamma by sin of theta. Right. So this is a trigonometric formula that has the analog in R2. And why is that? Because this basically you can argue using this that given any triple alpha, beta, gamma of angles that sum to less than pi, there is a unique triangle with side lengths defined using this kind of formula for C, A, and B that has the internal angles alpha, beta, and gamma. So in some sense, this is the analog. I mean, this is not an analog. This is basically saying that any triple you give me of angles that sum to less than pi, I can give you a triangle which is unique up to isometry that will have those angles. And I mean, yeah. So, and also that the angles uniquely define the side lengths, right? So there is no such similarity transformation as we are familiar with in R2. If you scale the sides of a triangle, you change the angles as well because of this. So that is more or less all I had to say about hyperbolic geometry. There is of course much more to do, and in fact people also speak of higher dimensions, H3 and all. But let's now move to hyperbolic surfaces. Right. So why did we do all this? That is what this next section will sort of motivate. Okay, we now sort of know how to do geometry in this abstract object H2 that we have defined. But well, it's useful. So what is a hyperbolic surface? So topologically, it's a surface S that admits inner product that assigns constant curvature -1, and it is a theorem that if chi of S is strictly negative, then S is actually hyperbolic. That is, there will exist some such inner product that will make it have constant curvature -1. This is essentially because of the fact that the universal cover, which we know to be homeomorphic to R2, we can replace with X2, demand this to be an say that okay, this should be an isometry, and sort of descend the metric from X2 onto S and get a metric. So that is what hyperbolic surfaces are in some sense. But I think a better motivation comes from Riemann surface theory. And so what is that? So for that we need a deep theorem. So maybe I should write that over here. Take another definition over here. The following is a deep theorem at the intersection of complex analysis and geometry. It's called the uniformization theorem. I think this is something well. It says that if you give me a surface, a Riemann surface S, which is simply connected, is this legible? Yes. It's legible. Okay. If it is simply connected, then it is conformally equivalent to one of these three. The sphere S2, which can also be thought of as CP1. So when we speak of Riemann surfaces, we sometimes call this the Riemann sphere, but it's just a sphere, but the complex structure. S2 or the plane C or the unit disk D. Right. So this naturally comes with a complex structure, and this we also have a complex structure inherited from here. But so what this should be thought of as is in some sense an analog of the topological classification. It's telling me that if you want to study simply connected Riemann surfaces, then it's enough to study these three. And in fact, there is a corollary which is not trivial. It requires some work that says that given any Riemann surface S, or S2 is this is covering of Riemann surfaces. Covers of Riemann surfaces. S2 is the universal cover only of itself. The plane is the universal cover of itself. The puncture plane C minus 0, and any compact surface which is homeomorphic to the torus T2. So why is T2 coming here? Because we can think of T2, which is usually defined as R2 mod Z2 as C mod lambda, for lambda any lattice sitting inside C. And the last is the most important thing. that D2 is the universal cover of every other Riemann surface. So what is this saying? This is saying that if you started any Riemann surface, you know its universal cover must be one of these three. Universal cover by definition must be simply connected. But what this theorem says is that apart from these four examples, everything else is covered by the unit disk. And so we can make another definition that a hyperbolic Riemann surface is any Riemann surface which is covered by the unit disk, which has unit disk as the universal cover. Now we have two definitions. How do we sort of compare them? Well, they turn out to be the same exactly because of the uniformization theorem and the classification of surfaces that I told at the beginning. We already know that the surfaces are SG and S2, right? So okay, so let's talk of surfaces without boundary for now. Then you can actually check that only S1 is covered by C and the other surfaces are only topologically covered by R2 because of something that I will show in a minute. Everything else seems to be covered by H2, right? And because we know that D2 and H2 are the same, at least at the metric level, it turns out that they are same as Riemann surfaces, and hence all the SG for G strictly greater than 1 turn out to be hyperbolic Riemann surfaces. And so these two definitions coincide, right? So, okay, so this is fine and dandy that we have this definition, we know this theorem, but well, what is a hyperbolic surface? What does it look like?
Well, I'll give you a construction now.
Any questions? I mean, I know there are a lot of questions. I haven't defined a lot of terms. At least you get some ideas. So the construction is as follows. Let's start with the torus. We know this is not hyperbolic, but then, so what we know from topology that the torus is essentially identifying this and these, right? If you quotient these out, then you get a torus. What you do is you tile the plane like this. I mean, this is an infinite tiling, and the tiling is in such a way that these are all compatible. So these are all identified with one thing, and these are all identified with one thing. Right. So what does this say? This is essentially a proof that the universal cover of the torus is the Euclidean plane, because when you identify them, this essentially sort of rolls over like this, and this rolls over like this, and all of these points collapse to one point on your torus, which sort of looks like this, right? So this is maybe your point. Basically, if you take this curve and unwrap it, you get one of these squares, but we can sort of think of it as unwrapping several times to give like an entire tile, right? So in Euclidean geometry, we know that the sum of angles around the point must be 2 pi, and we know that that happens because these are all 90, right? Even if it's not exactly a square, if it's like given by some parallelogram, the sum of angles of a quadrilateral of high school is exactly 2 pi, right? We know that. But, well, let's try and mimic this for the two-hole torus, right? It is this. It's a result, again from topology, that the polygon associated to a G1 torus is a 4G-gon. So, if I want to talk of S2, it should be an octagon. So, you can actually compute, I mean, the question is whether this is a Euclidean object or whether this is a hyperbolic object, right? In fact, we don't yet know whether it's a spherical object. It will be ruled out. If you could tile like the Euclidean plane with octagons, then any point will have 8 octagons sitting around it. Right? That's clear? Any point will have 8 octagons. But you can actually check that if you compute this internal angle, 8 times this theta would, I think, be 6 pi. Right? Yeah, I think this comes out to be 6 pi. Which is greater than 2 pi. So this is what is indicating that this is not a Euclidean object. In the sense that in Euclidean geometry, we cannot arrange for polygons where the internal angles of the octagon will sum up to 2 pi. And in fact, because it's not a Euclidean object, it's not also a spherical object, but it is in fact a hyperbolic object. And we have a very beautiful picture, which I don't think I'll be able to do justice, but let's try. Using what I said about hyperbolic geometry, you can actually prove that in the unit disk model, it's the same thing as the plane model, you can construct such an octagon such that these angles are all equal and sum up to 2 pi. So basically they are pi by 4 each. And when you quotient them in the sense that you identify this, just label it A, B, A inverse, B inverse, A, B, A inverse, B inverse, then these points will collapse and actually still be a point that has angles coming to 2 pi around it. So this is this sort of shows that your hyperbolic surfaces arise as quotients of H2. I mean, this is a visual proof, of course you can make this rigorous, but there's more, in the sense that we can actually show that you can extend this octagon to a tiling, in the sense that you basically mimic this in every one of these segments and do that for the segments there, and it will give you a fractal like tiling. Something.
I think when you are calculating between fundamental and between 4 element, right?
Yes.
So again, there will be 4 element.
Oh, I think this.
No. Everything was correct, just re-level this part.
It should be A inverse, right?
No. A, B, C is correct.
Oh, then it should be A, B,
No,
right.
A, B, A inverse, B inverse, C, D, C inverse, D inverse.
Yeah. So A, B, A inverse, B inverse. Yeah, now C, D.
Oh, yeah, well, that's not very important. Yeah. So it's arising as a quotient of H2, right? And this group gamma is the fundamental group, as he said. This is again covering space theory. And because it's arising as a quotient of this hyperbolic space, this gamma must turn out to be a discrete subgroup of the isometric group of H2. But we already know what that is. That's PSL2R. Right? So gamma is a subgroup of PSL2R which is discrete and also acts properly discontinuous. Right? So yeah, so I was talking about this tiling. So you can do this tiling, and in fact what you can do is you can argue out that there's actually r to the power 6 ways, in some sense of counting ways, of placing such octagons in a unit disk. And in general, for SG, there is r to the 6g minus 6 worth of ways of placing 4 gigons in the hyperbolic plane or hyperbolic disk to construct the SG, the genus G Riemann surface, because this is actually a visual proof that this is the Teichmüller space of genus C. But I won't define what that is. But yeah, so this is it. And so now we are essentially going towards. So now we are essentially going to focus on these groups, because we already saw that any a hyperbolic surface seems to arise by a quotient of H2 by some discrete group of PSL2R that acts properly discontinuously. We also have a converse that says that if you start with a subgroup of PSL2R which is discrete and torsion free, discrete and torsion free. So torsion free means that there is no elements of finite order, and discrete means that it's discrete as a subspace of PSL2R which has a topology from R4. Right. If you start with such a group, then the space X, so then you can show that such a group will always act properly discontinuously on H2. The space H2 mod gamma will have a unique Riemann surface structure such that the projection phi from H2 to X is a covering, or rather from in Riemann surface theory we call this phi to be a local isomorphism. Right. So this sort of says that any hyperbolic surface arises from H2, and these are all the hyperbolic surfaces. That's what this discussion says. So essentially what we have concluded is that to study hyperbolic surfaces, it's enough to study such groups that are subgroups of PSL2R which are discrete and torsion free. Well, we make this definition. Any group which is a subgroup of PSL2R and is discrete. So we don't include this torsion free condition for some technical reasons. We just say that hyperbolic surfaces arise from torsion free Fuchsian groups. Because it turns out that this definition is general enough to make stuff more interesting. Because okay, let's not get into that. Yeah. So this is the definition. So I hope that I have motivated why we are interested in this, because this to me at least feels a lot dry. Like why do we even care about such discrete subgroups of PSL2R in the first place? Because and well, this is the motivation that all hyperbolic surfaces arise from such groups, a subclass of such groups. Right?
Is the converse true?
Yeah, that's what this theorem was saying. That we already gave a construction that any SG was arising at H2 mod gamma, and this theorem says that if you start with a discrete torsion free subgroup, then this will have a unique such hyperbolic surface. That's what this converse is. Any hyperbolic surface arises as this, and that is all. There are no more hyperbolic surfaces. Yeah. So that's the definition. We want to understand these terms. How do we do that? Well, we understand them using the following classification of elements. I mean, we will give examples of this very shortly, but okay, maybe I should mention one example right now. PSL2Z, the modular group, is a discrete, not torsion free, but discrete subgroup of PSL2R, and hence is Fuchsian. And this is perhaps one of the most important things in mathematics. Yeah. So, yeah. Elements of PSL2R. So we want to understand Fuchsian groups by first understanding how elements of PSL2R look. So we already know that they look like matrices ABCD, A divided BC1, and we don't really care about the sign. So we define this thing, base of ABCD, where this now denotes the class of ABCD in PSL2R to be mod of A plus B. So why the mod? Because it can be minus A minus D, and we want the case to be positive. Right. If you have that, then it's a theorem. I mean, this is not really a theorem that if G is not equal to the identity matrix, in PSL2R, then 1, either trace G is less than 2, and so the fixed points of G lie in H2 itself. There are, okay. So if trace G, so how do we compute a fixed point? So note that G looks like AZ plus B by CZ plus D, right? So fixed points are simply computed by solving this quadratic equation. And you'll be able to show that this quadratic equation has positive real roots or complex roots exactly depending on this trace G minus 2. So if trace G minus 2 is negative, then the discriminant will be negative, and so fixed points will actually be complex, and there will be two distinct fixed points, both lying in H2. 2. If trace G is equal to 2, then there is only one fixed point, and that will belong to 1, and C is contained in R. And last, trace G greater than 2, then again fix G is as two distinct points, and it's still here. So we allow for infinity by basically saying that A infinity plus, in the sense that if C is not 0, then we can speak of the action of an element of infinity. Right. So that's how we do this. And then what we do is we say that if the element has trace less than 2, then we say that it's elliptic. If the trace is equal to 2, or rather if the trace is greater than 2, we say it's hyperbolic. And by analogy with conic sections, if it's equal to 2, we say it's parabolic. Right? This is just some definition. But the interesting thing to note is that this kind of classification, that either there's basically the fixed points lie in the domain, the fixed points, there's only one fixed point and it doesn't lie in the domain, and there's two fixed points not lying in the domain. This is the same kind of classification that happens in a general mapping class group as done by Nielsen and Thurston. That's called the Nielsen-Thurston classification of elements in the mapping class. So, yeah, that's sort of why, that sort of indicates why this theory is relevant in theory of mapping class groups, etc. How much time do we have? How much time? 20 minutes.
It's 15 minutes.
15 minutes. Yeah. So we have this theorem that one, any cyclic subgroup of PSL2R, which is, so the first step to understanding Fuchsian groups is to see what are the cyclic Fuchsian groups, and this is basically, this theorem basically does that. So we basically start with the cyclic subgroup of PSL2R. If it is generated by a hyperbolic or a parabolic element, according to this definition, then it is always Fuchsian. And if so, like this, if it's generated by hyperbolic or parabolic, then it's Fuchsian. And if it is generated by elliptic, then it's Fuchsian, if and only if it's finite. Sorry about this. Right. So, what is this basically saying? This is saying that this goes back to the thing that I said, that we basically, as far as hyperbolic surfaces are concerned, we only care about torsion-free subgroups, right? So note that elliptic elements are the only ones that can have torsion, because these hyperbolic and parabolic elements don't have fixed points in the domain H2, they cannot have some power that goes to the identity, because it's a discrete subgroup to begin with. right? And so this theorem says that if your gamma for the hyperbolic surface was taken to be cyclic, then it gives the proper hyperbolic surface if and only if it was generated by a hyperbolic or parabolic element. Because if it was generated by an elliptic element, it must have been finite because it was Fuchsian, and so it cannot have been a surface to begin with, because it will sort of wrap around and there will be points which won't satisfy the regularity condition, right? So that is what this is doing. And then you have another result. This sort of also makes that analogy strong. Some group is Fuchsian if and only if gamma acts on H2 properly discontinuous. So properly discontinuous action simply means that it will have no fixed points, thought of as a group action, and it like the stabilizers will be fine, right? I mean, some topological definitions can also be used, but yeah. So this is the sort of characterization that you have a Fuchsian group if and only if gamma acts properly discontinuously, and so again to go back to that kind of criteria, it will be torsion free if it is properly I think I have to say this does not imply that it does not have fixed points. The torsion free condition would then imply that it will also not have fixed points. So basically this in some sense characterizes all Fuchsian groups, because we can find Fuchsian groups simply by finding groups that act properly discontinuously, and this is one of the examples. There can be other examples as well. You start with any, so a hyperbolic element, for example, looks something like lambda 1 by lambda 0 0 upon computation. So you start with for lambda real, lambda positive, yeah, lambda positive. You start with any such element and take the cyclic subgroup inside PSL2R, then that will be a Fuchsian subgroup because of this theorem. And yeah, so this sort of, I mean, in some sense finishes Fuchsian groups. But I have this last interesting theorem because we have some time. I'll mention that.
So you are saying that only finite kind of groups are acting properly
Stabilizers. Stabilizer of points in H2 should be fine.
I think usually lambda not equal to 1.
Yeah. So last theorem takes some time. I'll just do the statement, but it sort of classifies all Fuchsian groups in something. Let gamma subgroup of PSL2R be Fuchsian. Then 1. So this will have 4 parts. Suppose gamma is finite, right? Then it must be cyclic, and gamma is generated by some elliptic element, which can be thought of as a rotation by 2 pi by n for some natural number. It is infinite but has no hyperbolic element. Then it is infinite cyclic, then it is still cyclic, infinite cyclic, but generated by a parabolic element, and has no elliptic element. So there does not exist an element in gamma which will be elliptic. 3. If gamma in
How do you define Fuchsian group? Just as a
discrete subgroup of Fuchsian group.
Yeah, no. We can use it there. I mean, torsion theory.
Yeah. So that's what I said, that you make a more general definition. You start with only discrete subgroups of PSL2R, and then when you impose the torsion free condition, you get fundamental groups of hyperbolic subgroups. You make a more general definition because this turns out to be more useful in number theory, for example.
Otherwise, that partition doesn't make sense because that has some torsion.
Yeah, exactly. So the interesting cases are basically 3 and 4. Gamma has a hyperbolic element G, but the index of G is finite. Then you have 2 subcases. Maybe I will not write, I'll just take it. The first case is gamma is infinite cyclic and generated by some hyperbolic element, maybe this or maybe some power of this. And the other case is where it has a subgroup of index 2 which is generated by some hyperbolic element. Right. So what are these cases? These cases are basically saying that if you have a finite Fuchsian, you know that it's some basically a group of roots of unity, nth roots of unity for some n. If you have an infinite group with no hyperbolic elements, because recall hyperbolic elements look like this upon proper commutation, with no hyperbolic elements, then it is still cyclic, it's infinite cyclic, is generated by some parabolic element and has no elliptic elements. 3. Gamma does have a hyperbolic element, but that element has finite index. Then either gamma is the full group generated by G essentially, or there is some other hyperbolic element of which this must have been a power that will have index 2. And the last case is the most interesting, which I should write down. Else, so in all other cases other than these 3, there exists a subgroup such that gamma prime is isomorphic to F2, which is the field group on 2 generators, and gamma prime will only contain hyperbolic elements. So what is this saying? This is saying that almost all the Fuchsian groups of interest have complexity at least that of the field group on 2 generators, which we know is immensely complex. And these subgroups have a name. These are sometimes called Schottky subgroups because of the fact that you essentially what you do is you first argue the existence of such a subgroup that consists only of hyperbolic elements, and then you use the ping pong lemma from geometric group theory and show that it must be a free subgroup on 2 generators. That's basically it. So yeah, thank you. Any questions? Yeah, go ahead.
How do you relate Aaratrick Basu to Teichmüller?
Yeah, so there is this result that if you start with any surface S and the moduli space of S, it will be isomorphic as a space to the Teichmüller space of S, quotiented by the action of mod S, which is the mapping term of S. So, and this action is properly discontinuous. And somehow this is exactly analogous to how given a hyperbolic surface S, that is or something. So somehow this is the analogy. There's of course a lot more to be done here because this turns out to not even be a manifold. This is in fact a manifold. R to the 6g minus 6 for S to be Sg. This is not even a manifold. But it turns out by the work of Thurston and others that the classification of elements in mod S is exactly the same. That is sort of the identity. Yeah. Any other questions?
Another thing about that G-dinar polygon, you mentioned that it can be instant circle in R to the power 6 minus 6g ways. I mean, what does this mean? Like, do you mean isometries or something?
No, it means in the sense that I'll be using a different chalk because I can't write I apologize if this is not visible to the people at the back. Means that we want this is somewhat visible. We want so tau g, which is tau of SG, is basically can be defined as height met of SG up to equivalence. So what is this? This is saying that we want to find out all the different possible ways of giving hyperbolic metrics on the surface SG up to some notion of equivalence. Let's not go into that. But we want different hyperbolic metrics in some sense. And that is what can be proven to be r to the 6g minus 6. So in some sense, there's 6g minus 6, r to the 6g minus 6 ways of putting genuinely different hyperbolic metrics on the surface of genus. And that can be seen using some heuristic dimension counts. But there are up to this 6g minus 6 degrees of freedom of real parameters of placing a 4g gone in the unit list. You basically count the edge lengths, the angles, because the angles sum to some 2 pi. You reduce something and then you have isometry action that reduces something that basically gives you a -1 and -5 basically comes from there. And this is basically because of the I think angle summing to 2 pi, and -5 is basically the isometry thing. I mean, in the sense that if you simply rotate the polygon in the disk, you get the same thing, right? So that is where the -6 is coming from. 6g comes from the 4g one. We have 4g many lengths and 2g other parameters. Yeah, that's the heuristic sort of thing. This can be made here. Any other questions? Yeah. Oh yeah, okay. I should mention references. So the first thing, of course, is you should know some topology. Without that, you are lost. So you can pick your favorite topology textbook here, algebraic topology. Then what I said about hyperbolic geometry and Fuchsian groups is essentially from Svetlana, Katok, Fuchsian groups, but this is somewhat of a dry book. A lot more algebraic. What I have studied is essentially from the first 2 chapters. There is a book by Farb Margalit, amazing book. A primer on mapping class groups. The first section or 2 will deal with hyperbolic geometry and surfaces and hyperbolic surfaces. But this takes a more, assumes you are a little more mature. And this last theorem, on the classification of Fuchsian groups, it's given in Katok in a different sort of way. This particular kind of approach is there in Hubbard, John Hubbard, Teichmüller theory, volume 1. First chapter, I think second or third chapter. First chapter is on the uniformization. Teichmüller theory, volume 1. Yeah. So these are basically all the references that I have used, but there are of course a lot more. Essentially, somehow a lot of Teichmüller theory boils down to study Fuchsian groups. So there's a lot of resources on Teichmüller theory that do this well. And hyperbolic geometry is a vast subject. There's a lot more to do in higher dimensions. A lot of Thurston's work is actually on hyperbolic geometry on 3 and 4 dimensions. So yeah. If nothing else, then we can end.
So I would like, so let's applaud the speaker.